All right, so now we're going to systematically develop more theory about continued fractions. And first I'll start with a quick review. In case you've forgotten everything. So we use the notation A0, A1, etc. up through A sub n to mean the fraction A0 plus 1 over A1 plus 1 over A2 plus 1 over dot 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 plus 1 over A sub n. And you can also continue this on indefinitely, and then it means the fraction that goes on indefinitely, which in a moment I'll... Whoa. Excuse me. Thanks. And I'll prove in a minute that if the a sub i's are integers that are non-negative, then except for a0, then this converges. So that's the first thing we're going to carefully prove. And we call this continued fraction simple if the a sub i's are all integers. And we always assume that the a sub i's for I greater than or equal to 1 are positive integers in the case when it's simple. So, but we always assume they're positive for I greater than or equal to 1. The first one can be negative, but all the others have to be positive. Otherwise, the theory doesn't work out very well. And a key thing we did was define some numbers Pn and Qn, which simplify all relevant algebra a lot. So they're defined as follows. The recurrence and P minus 2 is 0, Q minus 2 is 1, P minus 1 is 1, Q minus 1 is 0, P sub 0 is A0, Q sub 0 is 1, and then in general, P sub n is A sub n, P sub n minus 1 plus P sub n minus 2, and Q sub n is A sub n, Q sub n minus 1 plus Q sub n minus 2, and moreover, the main thing that we proved about these is that the value of the continued fraction a0 up through a sub n is just p sub n over q sub n. Moreover, in the case when the a sub i's are all integers, so it's a simple continued fraction, then this gives the reduced form of the fraction that's the value of this continued fraction. The numerator is p sub n, the denominator is q sub n, in reduced form. We also proved some things about the differences of the successive Pn over Qn, that is the successive convergence. So we'll use the notation C sub n often to denote the nth convergent of a continued fraction. That is what you get by taking and evaluating this fraction up through a sub n. And so the thing we proved by induction is that P sub n over Q sub n minus P sub n minus 1 over Q sub n minus 1 is equal to minus 1 to the n minus 1 over Qn minus 1. Let me make sure that's right. Yep. And then we also proved, actually we didn't prove this, but a very similar argument tells you that P sub n minus P sub n minus 2, so P sub n over Q sub n minus P sub n minus 2 over Q sub n minus 2 is minus 1 to the n an over Qn minus 2. So a similar induction implies that. Okay, so I'll keep all of this on the board since it's what we'll use to prove everything else. Okay, any questions about this? So basically from first principles, everything should be defined here that we're talking about. Given given numbers, a0, a1, etc., the reals, you get some expression like this, assuming that the a sub I are positive for I greater than or equal to 1. And given these numbers, you can define pn's and qn's via this recurrence, and they give the numerator and denominator of this fraction if you were to sort of simplify this whole thing using rules over arithmetic. And now, let's see what we proved so far. First, we proved that every rational number, if alpha is a rational number, then alpha has a continued fraction representation, which need not be unique, but it's almost unique. There's two possibilities where there's one situation where you can have a slight failure of uniqueness, but it's very close to being unique. So you have alpha equals that for some simple continued fraction. And the way you find the a sub i's in this is you just use the Euclidean algorithm to find the GCD of the numerator and denominator of the rational number alpha. You take those two numbers, the GCD at the end is just 1, but if you look at each step in the Euclidean algorithm, there's a partial quotient that appears. And that sequence of partial quotients that pop out of the Euclidean algorithm are exactly the a sub i's right here. That's why these are called the partial quotients. So that's what we did last time. The second thing we did last time was considered an arbitrary real number, often r, which is not a rational number. And then we wrote down a sequence of numbers a sub I as follows. So you just take alpha and you write it as a0 plus t0, where a0 is an integer, positive or negative or 0, and 0 is less than t0 is less than 1. That's the fractional part. And now you take 1 divided by t0, and you write that as a1 plus an integer, or an integer a1, which is now positive, plus t1, where t1 satisfies that condition. So here a1 is in z, it's greater than 0, and 0 less than t1 less than 1. And you just continue this process, consider 1 over t1, and that's a2 plus t2, where a2 is an integer that's positive, and 0 less than t2 less than 1. So you continue this process, you get a sequence of integers, a0, a1, a2, etc., and they give you a continued fraction. The thing I didn't prove, which will take a little bit of work, well, it's a bit of work. We're going to prove that that continued fraction is, when you evaluate it, that is, if you take the limit of all the partial convergence, it gives you alpha back. So every real number has a continued fraction representation. That's the main thing we're going to prove today. Before I prove that, though, I'm just going to prove a little observation about a continued fraction. So we'll prove some lemmas. So this is the review. We're done. Section 1 review. Section 2, I'm going to talk about convergence. So now consider a continued fraction, a0, a1, a2, etc., which goes on forever, and it's simple, by which I mean that all the a sub i's are integers, and the a sub i's for I greater than 0 are positive integers. Okay? This continued fraction converges in the sense that if you were to truncate it at some point and evaluate the whole thing, the rational number you'd get would be some number, c sub n, and if you kept doing this for larger and larger values of n, the sequence of rational numbers you get would converge to a specific real number. Okay? So let's prove that very carefully with no gaps at all. Alright? Ready? So let's define it over there. C sub n equal a0 through an. It's a specific rational number. So proposition, the limit as n goes to infinity of c sub n exists. Okay? So you don't just bounce around and get weird rational numbers as you go. You'll get lots of rational numbers, but you get closer and closer to some definite real number, like pi or something like that. Okay? So to prove this, I'm going to write down some observations that are a little tricky to prove, which we'll prove, that are really just corollaries of what we did before with the Pn and Qns. And then it'll be very easy to read this proposition off. Okay? So before proving it, let's prove a lemma or two. Okay, so here's the lemma. So be careful, it's a little tricky. You take the subsequence C sub 2n, that is the convergence where the index is even. This subsequence is an increasing sequence. And similarly, if you take the subsequence of convergence, these rational numbers, where the subscript is odd, that's a decreasing sequence. So knowing these two facts once we prove them, and they'll follow very easily from what we have right here. Not surprisingly, look at this. I mean, it just says the difference of two of these convergence, somehow every time one of them is greater than the other. That's the sort of thing we get out of this, okay? So we'll do that carefully. So once we do this, it won't quite give us that the limit exists, because you might have that these all increase to something and these all decrease to something, but they're different things. So there's one other thing that we need that will not only tell us that these converge, but that they converge to the same thing. And it's actually the trickiest part to prove. So, and all the even ones, every single one, is less than any of the odd ones. So C2n is less than C2n plus 1 for all n and m. Okay, let's prove this. Then it will be really easy to see that this limit exists. Once we have that, it'll be fairly easy, again, to see that alpha is the limit of that continued fraction. Actually, I mean, technically, when I prove that alpha is the limit of this continued fraction I defined right here, I'm going to give that proof and it's not going to use this. But at least this will tell us that if you take any continued fraction at all, you get a real number. And on the other hand, given any real number, you get a continued fraction. So you see that you kind of have this thing that goes back and forth, just like real numbers correspond to decimal expansions up to some very minimal equivalence. Okay? So you can think that we're proving that you can think of continued fractions as an alternative way of thinking about or writing down real numbers. So real numbers, some set, the set R of real numbers, and you can think about them in terms of equivalence classes of decimal expansions, but also in terms of equivalence classes of simple continued fractions. Okay, so that's the picture I'm trying to theoretically draw in your minds. Okay, any questions before we start proving stuff? All right. So it's really good to start with these two statements because they're just easy consequences. So in my notes, I wrote trivial, so let's see why. So first, let's look at the first statement. The C sub 2n increases. So all you have to do is, what this says is that if you take an even subscript right here, and then look at the previous one with an even subscript, that would be right here, then the difference is positive. That's what it would mean for the sequence to increase. That if you take something and then you take the previous one in the sequence and take the difference, it's positive. But this is a formula for the difference. So what we're doing is, here n is twice m, say. So n is even. You take the difference, it's minus 1 to the n, but the n is even, so that's just plus 1, times a sub n. The a sub n are all positive except possibly the very first one. So don't worry about the first one for the moment. But if we're looking, so don't worry about the first one. So this is some positive number, and then the denominators are positive because look how these things are defined. So let's see, Q0, Q1 involves A1. A0 is never involved in the definition of the Qs. The only possible AI that can be negative isn't even involved. And you're just adding together previous ones with some positive coefficient. So the Qs are all positive. And so this number over here is always positive whenever you're considering one of the differences. Therefore, the even ones just have to get bigger and bigger. Okay, so now a very similar argument will tell us that the C sub 2n plus 1s, that is the C sub n's where the subscripts are odd, decrease. Okay, so think about it. If now n is 2m plus 1, you take the difference of two successive partial convergence, C sub n, and it's equal to -1 to an odd number times a positive number. So it's always negative. If you take something and the next one in a sequence and it's always negative, that means the sequence is strictly decreasing. So there you are as well. Okay. And if you try this in practice with particular examples, you'll of course also see that this is happening. The plots look like this, just kind of bouncing back and forth, where you have the odd one. That wasn't a very convincing plot of anything, but if you look in the book, I drew some nice plots. Okay, so any questions about this? The quick summary is the hard work we did over here to prove this, which was simply induction, nothing more, just prove it for the base cases, then check that knowing it for one implies it for the next. That implies directly this statement right here. Okay, now let's do a little more work to check that all of the even ones, every single even subscript one is strictly less than every odd subscript one. Okay? So we're done with the first part. Now let's do the second part. So I'll call this part 1, and I'll call this part 2. So this is a little bit harder, and we're going to have to consider 3 cases. I'll do it right here so we have more space. So I want to use the same letters I use here. So C sub 2m plus 1 less than or equal to C sub 2r. Imagine that horrible thing happened, i.e. this was false. So if this happens for some m and r, positive non-negative integers, then, okay, we just have to show that there's no way that this could ever happen. And then that will mean that we always have that the even ones are less than the odd ones. Okay? So there are a couple of possibilities. These are 2 integers. Either one of them is less than the other one, or the other one's less than one of them, or they're equal. So those are the 3 cases we're going to consider. The easiest one is when they're equal. So then either m equals r, or r is less than or equal to m, well, okay, strictly less than m, or r is strictly greater than m. Those are the 3 cases to consider. Okay, so I'll just argue in each case that this gives us a contradiction, and that will tell us that all the even ones have to be strictly less than all the odd ones. But then the even ones are increasing, the odd ones are decreasing, so you have the even ones increasing, but they're all smaller. The odd ones are decreasing and they're all bigger. So actually that isn't quite enough to see that they converge, but you know that at least the even subsequence has to converge to something because it's bounded above by all the odd ones. And conversely, or in addition, the odd sequence of decreasing ones has to converge to something because it's bounded below by all of these even ones. But it could still be that they converge to 2 different things. But all we'll need is to show that they get really close to each other, which we'll do in another step, and then we'll see that this holds. Okay? So this isn't enough to prove that. Otherwise I wouldn't have separated out. This would just be the proof of that. Okay, so let's do it. So we'll just check this first. It will be useful. It will make it easy to prove the proposition. Okay, first, suppose that m equals r. So then, let's just let n be 2m plus 1. And, right, so we're going to use, what this says is that c sub n minus cn minus 1 is minus 1 to the n minus 1 over qn minus 1. So we're going to take that n and substitute it in here and see what it tells us. So supposing that m equals r, so what that means is that that number m right there is that number r right there. So then this says that c sub n is less than or equal to c sub n minus 1. Right? That's exactly this inequality. if m equals r, then the subscript here is 1 bigger than the subscript there. Okay. Now the difference, cn minus 1, is given over here, but the n is odd, so that's actually a positive number. So cn minus 1 is equal to minus 1 to the n minus 1 over something positive. With that subscript, n minus 1, n is 2n plus 1, so that subscript is even, so it's minus 1 to an even, and so this is positive, and so that's a contradiction, because cn is actually strictly greater than cn minus 1. Ooh. So that can't happen. So the case m equals r can't happen, and all we have to do is roll out these two other cases, and then we'll conclude that none of these cases happen, so this doesn't happen, so this is always the case. Okay, that's the logic. Okay, let's do the other two cases. So there's a trick for each. It's basically the same. So now we're assuming that r is less than m. So again, you have these two numbers. This inequality holds, and we're assuming that r is less than m. So we're going to write it as follows. We have c2m plus 1, which is less than c2r by assumption. And this is less than or equal to c2m. Why is that? Well, r is less than m, and we already proved that the c sub even subscripts thing is an increasing sequence. And in fact, because it's a strict inequality, I just make it strict. So c2m plus 1 is less than c2r by assumption. c2r is less than c2m by what we just proved in 1. But wait, now we have c2m plus 1 strictly less than c2m. And didn't we just rule out that happening? We just proved that that can't happen. So we just proved that this is impossible. So contradiction by m equals r case. And now let's do something analogous to this, but of course we'll use the other one for the bottom. So assuming that r is greater than m, we're just going to write again the inequality. So c2r plus 1 down less than or equal to c2m plus 1 less than c2r. So we claim. So this is from 1 again. Whenever you take a smaller, so the m is smaller, and so remember for the odd ones, it's a decreasing sequence. So when the index gets bigger, the number gets smaller. And here the index is bigger. c2r plus 1, that has a bigger index than the other one, so the number is smaller. And c2m plus 1 is by assumption less than c2r. Well, okay, it's less than or equal. Okay, but exactly as before, c2r plus 1, or sorry, c2r plus 1 can't be less than c2r, because we proved in the first case that you can't have that. So when m equals r, we got a contradiction whenever we had c2r plus 1 less than or equal to c2r. That can't happen. So again, it's by the first case, by m equals r case. This notation means contradiction. Okay, so in every case, this led to a contradiction. Hence, you really have that all the even ones are less than the odd ones. That's it. It's the sort of thing that would just be really hard to check based on the algebra of this, but it's really easy once we write down these formulas and do the induction. Okay? If you got completely confused, at least consider that it should be easy, given that you have these sorts of formulas that switch sign every time. It should be really easy to figure out how subsequences behave. Okay? If you sat down in a room and thought through it carefully. Alright, so let's prove the limit exists. And for this, we're just going to note that the c's get closer and closer to each other. Okay, so let's finally prove this. Proof. So we have the subsequence C sub 2n of even ones, and it's getting bigger and bigger. So here's what the even ones are looking like. And then we have the subsequence of odd indexed ones, and they're getting smaller and smaller every time. So if you take any one of the even ones, then it's a lower bound on the sequence of odd ones. And if it's a fact from calculus that if you have a sequence that's bounded below and decreasing, it has to converge, right? Because if it diverges, well, I mean, you know this. Okay, so we know that these two subsequences converge to something. So limit c n goes to infinity, c sub 2n exists. Limit n goes to infinity, c sub 2n plus 1 exists. And what's the relationship between them? Is the first one bigger than or equal to the second one, or the other way around? Is limit as n goes to infinity c2n, is it greater than or equal to, is this true or not? Is that true? No.
Should be the other way.
Should be the other way around. Yes. Every single one of these even ones is less than every single one of the odd ones. And so the limit is going to be less than or equal to the limit of the other one. Okay, so you have two numbers, one is less than or equal to the other. And those two numbers are the two limits here. So now all I have to do is convince you that those two numbers are arbitrarily close, and then you'll have to believe that the limit of the whole sequence exists. Okay, so here's what we'll do. We'll just look at this. Look, if you take the difference of any two successive convergents, in absolute value, it's qn times qn minus 1. Remember these numbers q sub n, they're given by the formula right here. They're like Fibonacci numbers, except even worse, because these a sub n's can be bigger than 1. So these numbers grow very, very quickly, like Fibonacci numbers. So this denominator is huge. And it's also the difference between an odd and an even. So you have all of these, this subsequence of even ones going up. You have the subsequence of odd ones going down. And if you look at the nth one, it's getting really, the difference between the nth ones of both of them, they're getting really, really, that difference is getting really, really small. And so for each n, the difference between these two numbers is, let's see, erase something here. So I'll just note that the absolute value of c2n plus 1 minus c2n is equal to 1 divided by qn times, or sorry, not qn, but q2n plus 1 times q2n, and that this goes to 0 as n goes to infinity. And that implies that these two limits have to converge to the same thing. These two sequences converge to the same thing, or these two limits are the same. Okay? And that proves this proposition. Any questions about that? You have questions at all? You have to ask a question. You could ask, yes?
What question should we ask?
Here's an example question. This is so ridiculously obvious. Why? Or, wow, this is completely confusing. Why? Those are two questions you can choose from. Surely one of the two is a question you might have. What?
This is completely confusing.
That's a good question. I think it's confusing because, as is the case of all proofs that you'll ever see, it's extremely hard to follow tedious details of proofs with all details given and somebody else is giving the proof. Just the way it is. It's much easier to follow proofs yourself. I think that's why it's confusing. Either that or I'm really bad at explaining things. Which is entirely possible as well. Usually when you talk in front of a bunch of people, you don't give many details of proofs, and so you convey something. On the other hand, when possible, one thing is that I'm not leaving out anything here. So it's pretty much as long as you know the basic facts from calculus, you should believe this conclusion if you follow the steps. One thing is every detail of this is also in the book, so you can read this proof as well. My hope is that if you're getting confused right now, when you go and read it in the book tonight, you'll find it extremely easy to follow because of the discussion in class. It's also potentially confusing because it's kind of like calculus, but completely different. And you're probably not used to continued fractions. Great. So just different. Maybe some of you are. But I don't know. Okay, so how about this? Real numbers. So let's prove that this procedure right here that assigns to any real number its continued fraction expansion gives you a continued fraction that converges to that real number. Plenty of time to do that. So just to summarize what we proved just now, we just proved that there's, like in a more kind of abstract way, if you take the set of continued fraction, simple continued fractions, A0, A1, so basically these numbers, etc. Expressions like this, there's a map from that set to the set of real numbers. So this map exists. That's what we just proved. It's a natural thing. And the map, of course, is take the continued fraction, take the numbers, and evaluate that continued fraction. And you get a real number. The fact the sequence that we were considering converges tells you that that real number exists. And now what we're going to do is the other direction. We're going to prove that there's a map the other way. Given any real number, there's a continued fraction representation of it. So, composition given alpha in R, say alpha is not in Q, otherwise the procedure below terminates. We have alpha is equal to the value of the continued fraction that you get via this procedure right here, this, as given. Because a priori, maybe you just get a whole bunch of numbers from continued fractions, but maybe there's some notion of super transcendental or something where there are real numbers that can't be represented by a continued fraction. So you could worry about that, but it turns out that's not the case, as I'm going to prove. This is slightly tricky, a little bit more tricky than you might expect, but it's just a calculation. So here's how we'll do it. Proof. So alpha is equal to, let's write something down and I'll think about it for a minute. The finite continued fraction A0, A1 up through AN, and then 1 over Tn. Notice this 1 over Tn is just a real number that will be strictly greater than 1. So this is not a simple continued fraction because one of these is not an integer, but it's okay, you can still write it down. It means A0 plus 1 over A1 plus 1 over A2, etc., all the way up to that. And it's pretty, we have already proved that this holds, but just to give you a sense, again, if you don't remember, let's just look what happens if you write out what the first 3 steps here mean, and it will be exactly this with n equal to 3, or n equal to 2 actually. So this just says alpha equals A0 plus T0, which is A0 plus 1 over T0. But 1 over T0 is A1 plus T1. But you can write that as 1 over T1. And 1 over T1 is just A2 plus T2. So this is A0 plus 1 over A1 plus 1 over A2 plus 1 over T2. And that's exactly, this is just the continued fraction A0, A1, A2, 1 over T2. Okay, so that's why this is true. And now, with this in hand, what we're going to do is compute the difference, alpha minus C sub n, where C sub n is by definition, again, just what's given here. C sub n is the rational number, which is the continued fraction A0 up through AN. So we're going to compute this difference, alpha minus C sub n. And what we're going to see is that it's really small as a function of n. And if we prove that the limit as n goes to infinity of alpha minus Cn goes to 0, then we'll know that the limit of the Cn's is alpha. And that's what we want. Moreover, as a corollary of this, we're going to get a precise statement about how close alpha is to Cn, which is exactly what we want in order to know how good, say, pi is represented by 22/7 or any of these rational approximations to pi. Okay, so let's just compute this. And this is, the way to compute this is to use the definition of the p sub n's. So this is equal to p sub n plus 1 over q sub n plus 1 for this continued fraction. So p sub n plus 1 would be, it's pn times the last thing, 1 over tn, plus pn minus 1, divided by qn times the last thing, 1 over tn, plus qn minus 1. Remember, this algebra holds irregardless of whether this is a simple continued fraction or not. It's just for real numbers. And remember, I told you every single thing we prove with continued fractions is going to use exactly this thing right here. So this was just by induction, and it was the thing we did at the beginning, and it's the statement that everything relies on. The fact that Cn is equal to Pn over Qn, or you define them this way. Okay, so now let's compute alpha minus Cn. Cn is the continued fraction A0 up through An, but it's also Pn divided by Qn. So look, alpha minus Cn is alpha, which we just got, Pn times 1 over Tn plus Pn minus 1 over Qn times 1 over Tn plus Qn minus 1 minus Cn, which is just Pn over Qn. The second you see this, I hope, you should almost feel like you've just been pushed and now there's a bunch you have to do and you can't stop yourself. You may get completely confused as I do it, but just seeing this, you have to feel there's something that you just got to do, right? It's like you just got tossed over the side of a roller coaster and now you're going to go. By which I mean, there's something to be simplified here. All these numbers, they satisfy various inequalities and stuff now. There's all kinds of facts about them. We're going to be able to get something out of this. Okay? It's just going to be, now we just have to add a little effort and see what happens. So let's do it. So what I'm going to do is just add these together and then see if anything nice cancels. Hint, something nice will cancel. And then look to see whether any induction thing we did before pops out. Yes, it will. Boom, we'll get what we want. Okay, so do the arithmetic. This is, I'm just going to subtract fractions, so numerator times denominator minus denominator times numerator. So Pn times 1 over Tn times Qn plus Pn minus 1 times Qn minus the other one, Pn Qn times 1 over Tn plus Pn Qn minus 1 divided by the product. And I won't get too aggressive with the product, just Qn times 1 over Tn plus Qn minus 1 times Qn. First, does anybody see anything that cancels? Any better, because there's something pretty annoying that cancels.
Qn over Tn.
Yep, look, Pn Qn divided by Tn minus Pn Qn divided by Tn. Boom, we get to get rid of that big annoying thing. And look what's left over, Pn minus 1 Qn minus Pn Qn minus 1, which is exactly what this is about right here. Just multiply both sides through by Qn minus 1. So we're going to be in really good shape. So So just rewriting this, it's Pn minus 1 Qn minus Pn Qn minus 1 divided by Qn times something that's bigger than 1, namely 1 over Tn, plus Qn minus 1 times Qn. This denominator is really, really big. This numerator is a power of minus 1 divided by something, or actually just a power of minus 1. If you multiply both sides of this through by Qn minus 1, you get exactly what I have here, up to sine whatever. So this is equal to minus 1 to the, so when you do that, multiply both sides through thing, you get the negative of this, so I'll just put minus 1 to the n, divided by Qn times 1 over Tn plus Qn minus 1 times Qn. And remember, Tn is a little positive real number, so 1 over Tn is some number bigger than 1. Positive number bigger than 1. So what do we have in the bottom? This thing at the bottom is just really, really big. The thing on the top is plus or minus 1. So if you take the difference of these two numbers, for n large, it's as small as you want. So alpha has to be the limit of the C sub n's. So this goes to 0 as n goes to infinity. Okay? And in particular, alpha must be the limit of the C sub n's. So alpha is equal to the limit as n goes to infinity, C sub n. So now we know both directions. We have maps in both directions. The continued fraction procedure takes a real number as input and gives you back a simple continued fraction representation of it. Given a simple continued fraction, there is a number you get by taking the limit of the partial convergence. So there's a different way of looking at real numbers than you may have had experience with so far. So far you have decimal expansions. A real number is basically a decimal expansion, up to the fact that 0.99 and 1.00 are the same number. But here you have yet a completely different way of looking at real numbers. And here it's different. With decimal expansions, the ones that repeat are exactly the rational numbers, and then all the other ones don't repeat. With continued fractions, the rational numbers are exactly the finite the continued fractions that truncate after some point, they're just finite. The ones that repeat will turn out to be the quadratic irrationals, and the ones that don't repeat are everything else. So I will summarize that last statement, and then we'll be done. By the way, there's a corollary to this that I better state, I just promised it to you. Alpha minus Pn over Qn in absolute value is less than 1 over Qn times Qn plus 1. So this tells you that, like when you look at the continued fraction expansion of pi, that if you take the nth one, this automatically tells you something about what this difference will be. And there are other results which tell you things about the best rational approximation to a real number with given bound on the denominator is attained by this, but that's beyond what I'll be talking about here. Okay, then finally let me, this corollary isn't completely obvious, it's proof in the book. I wrote the proof down in one line here, but I think I'm going to leave it for you to read in the book. Now I want to summarize what I said in words a second ago, and then we will prove the quadratic irrational business. That is, we'll completely understand the eventually repeating continued fractions first thing on Wednesday. Okay, so here's the picture. You have real numbers, which you have probably often thought about in terms of floating, in terms of decimal expansions. Decimal expansions being a representation of real numbers, but you also have real numbers now represented in terms of continued fractions. And with decimals, the eventually repeating ones, those correspond to rational numbers. And with continued fractions, the finite ones correspond to rational numbers. And then over here you have this sort of a whole new level, namely you have repeating, and these correspond to roots of quadratic polynomials. So roots of quadratics. So in other words, something like 1 plus 7 square root of 3 over 18. If you compute the continued fraction of this number using the continued fraction algorithm, you'll find, amazingly enough, that it repeats. It has some period. It has some funny stuff at the beginning, and then it starts repeating over and over again. We're going to prove that that happens. That's our next goal. Okay? So now we're done. So this is our immediate goal. Again, if anything was totally confusing to you, every single thing I said more or less is in the book, and you can just read it carefully. By Wednesday. Josh, do you have a question? You mean like E? That's pretty mysterious. When there's a pattern, but it's not repeating. It's pretty mysterious.